Hi everyone, welcome to Power Electronics, and this is the last session for the Power Electronics. We covered almost all the required topics for the Power Electronics. So in this video we are going to discuss about some questions from the DC to DC converters and some of the things like from the gate exam with respect to the SMPS. Okay, the first question is, in type A chopper, given that source voltage be 100 volts DC on period 100 microsecond, off period 150 microsecond, and load resistance 2 ohm, inductance is 5 millihenry with back EMF 10 volts connected in series for the continuous current conduction. The average output voltage and average output current will be respectively. So that's what. So remember, what are the step down chopper we discussed? Okay, step down chopper. Step down chopper, that is also called as type A or first quadrant chopper. First quadrant chopper. Okay, don't confuse if you are having any of this type A or first quadrant chopper. So both are same, okay, as a step down chopper. So now here the load is given. Whenever we are getting the kind of like chopper circuits, first we need to look at that what type of chopper is given. Second, we need to look at that what type of the load is connected to that. And then we need to look at what is the conduction, whether it is a continuous current conduction or discontinuous current conduction. But here in this case it is given RLE load and continuous current conduction. RLE load and continuous current conduction. Okay, in this case we need to calculate V average. V average is nothing but D times VDC. Okay, and we need to calculate I average. I average is nothing but V average minus back EMF by resistance. So these are the things we need to calculate here. That's what it is given, that average output voltage and average output current. So to calculate this, first we need to calculate duty ratio. How to calculate the duty ratio? So duty ratio is D equal to T on by T on plus T off. Okay, so in this case already T on T off already given. We need to substitute and get the duty ratio. Okay, it is 100 microsecond divided by 250 microsecond, then duty ratio is 0.4. So from that we need to calculate average output voltage. That's nothing but 0.4 into 100 volts. So that means 40 volts. Then we need to calculate I average. I average is nothing but V average 40 minus back EMF, that is given 10, divided by resistance, that's given 2. So that means it is 15 ampere. Okay, next, moving on to the next question. So in this case, chopper is employed to charge a battery as shown in figure. That means like this. The charging current is 5 ampere. Okay, that means I naught is already charging current or average load current, or I naught is same. Duty ratio is 0.2. That means we are operating the chopper with the duty ratio of 0.2. The chopper output voltage is also shown in figure. That means this output voltage waveform is given. Peak to peak ripple in the charging current is. Okay, that's what we need to calculate. So here this chopper circuit is there. That is nothing but like, instead of giving entire circuit, it is given with a simple representation. But if you want to take that entire representation, means it is like DC source, then switch, whatever the switch we are using, then diode, then inductance and back EMF. Okay, so this inductance is actually given here to control the charging current. So this is operating at a rate of duty ratio is 0.2. and this is DC. Here like a source voltage I'm taking, like this is actually given as a load voltage across the load. Instead of taking VDC, I'm representing this as a V0 because V represented as a V0. So this will be taken as a V0. Okay, so then this is VDC and diode. Inductance is given and load current, average load current is also given 5 ampere. So now we need to calculate what is the peak to peak ripple in the inductor current. That's nothing but delta IL we need to calculate. To calculate the delta IL, first we need to find out what is the load current waveform. So once you know the load current waveform, we can do that. So when you turn on the switch, that means it is running like this, then this diode is open circuited. In that case, you can see that the current flowing through the load or through the inductor. So that is actually decided based on the voltage appear across the load. Inductor. Voltage appear across the inductor is nothing but source voltage minus back EMF. So source voltage is DC, back EMF is also DC. That's why voltage appear across the inductor is also DC. When DC voltages appear across the inductor, then obviously current will be linear. That's what we discussed in SMPSS also. So that means this is linear current. Now when the switch is off, then this inductor current is forcing the diode to be turned on. In that case, again back EMF will appear here. That's why whatever the energy is actually available with inductor will be supplied to the back EMF. That means inductor voltage is nothing but back EMF. So that is also constant. That's why current will also be linearly changing. That means this current is actually linearly decreasing to min value, then again increasing to max, then like that and all. So this difference is nothing but delta IL. Okay, that is what we need to calculate. Okay, this is actually you can directly calculate using our SMPS formula, or otherwise we can derive again, not an issue. So that delta L is nothing but voltage appear across the inductor is nothing but L into di by dt. As I told you that di by dt will be taken as a change in current divided by change in time when the current waveform is following linear waveform. Okay, so during T on you can take or T off you can take, whichever it is possible we can take, that's not an issue. So during T on, the voltage appear across the inductor is important. That means when the diode is not in conduction, this switch is in conduction, the voltage appear across the inductor is nothing but source voltage minus back EMF. So that's why VDC minus back EMF equal to L into change in inductor current, that is what we need to calculate, divided by time taken to happen this change from minimum to max value, that is nothing but T on. Okay, so T on. Similarly, you can calculate for T off also. During T off, what is the voltage appear across the inductor? That's nothing but back EMF. Then we need to change the formula accordingly. So from this, change in inductor current IL is delta IL is VDC minus back EMF into T on by L. So now substitute everything and get the values. Delta IL equal to VDC. You can see that it is nothing is given VDC here, but from the waveform, okay, from the waveform, when switch is on, voltage is actually measured, V0 is measuring across inductor and back EMF. That's what here. So that is given as a 60 volts. That means VDC is given as 60. 60 minus back EMF is given here in the question itself. 12 into T on is given 200 microsecond. Okay, so that means 200 divided by L. L is given 20 millihenry. 10 to the power of minus 3. Here 10 to the power of minus 6. Okay, that we need to calculate using. Okay, so this is equal to 0.48 amperes. Okay, so this gets cancelled 10 times, minus 3 gets cancelled minus 3 times, that means minus 3 into 10 minus 2, that means It is 48 divided by 100.48 ampere. Then move on to the next question. Figure shows a chopper operating from 100 volts DC input. The duty ratio of the main switch S is 0.8. The load is sufficiently inductive so that load current is ripple free. That means load current is almost constant. That's the meaning of that. Ripple free is nothing but it's a constant. So ripple free is nothing but delta IL is 0. Okay, so that means load current is constant. The average current through the diode under steady state is, that means we need to calculate what is the diode current. We already discussed that. So waveforms, and then we derived the formulas also. If you want, we can discuss again. That's nothing but if the load current is constant, assume at I0. Now this load current is contributed by two things. When switch is on, the switch, that means diode is off. That during that time source supplying the load current. So during that time source current is supplying that load current, same thing I0, that is during T on. Okay, then again when switch is off, to control the output voltage, this load current actually forces the diode to be turned on. In that case, this inductor is actually supplying that load current again. So that means during this period it is 0, then again it will be I0, then it is 0, and so on. So here diode current is opposite. That means it is 0 when switch is on, and it will be I0 again when switch is off, and so on like that. So this is again I0, but this current is, so this is load current, this is source current, and this is diode current. Okay, so from this, for one time instant, if you look at here, this is T. Out of T, this is supplying only for T off. So using that, we already discussed average diode current is nothing but 1 minus D times I average. So what we need to calculate from here? First we need to calculate I average. What is I average? V average divided by resistance. How to calculate the V average? This is step down converter, that's why it is D times VDC. So that's it, top to bottom approach, then you will get the things. Okay, so in this case we'll calculate V average first. So V average is nothing but duty ratio 0.8 multiplied with source voltage 100. Okay, then it is 80 volts. Then I average, so I average is nothing but V, because it is a RL load, it is V average divided by R, that's nothing but 80 divided by resistance is 10 ohm, that means 8 amperes. So from this, diode average current is nothing but 1 minus 0.8 multiplied with 8, so that means 0.2 into this, so 1.6 ampere. Remaining current is supplied to the source when switch is on. That's why if you want, you can take that DC average current or average value of the switch current is remaining, that's nothing but 6.4 ampere. Okay, moving on to the next question. An ideal chopper operating at a frequency of 500 Hz supplies a load having resistance of 3 ohm and inductance of 9 millihenry from a 60 volts battery. The mean value of the load voltage for on-off ratio 4:1, assuming that load is shunted by perfect commutating diode and battery is lossless. So simple thing, it is RLE load and it is ideal chopper. Remember, nothing is specified about any chopper, it is a step down chopper. So that's what we need to remember. So here ideal chopper means step down chopper and the load is RLE load, and assuming load is shunted by perfect commutating diode, that's nothing but load is having a freewheeling diode and battery is lossless, nothing but we are having kind of continuous current conduction, everything. So now here we already discussed the similar type of question in the first example itself, but what is the difference between these two is why I have given this one is just because of only this one. Remaining things we can carry on, but I just wanted to tell that how to calculate the duty ratio. So when duty ratio is given just like on off ratio like this, it is nothing but simply 4 divided by sum of those two. Okay, so that's it, 0.8. So remaining things you can calculate based on the given things. Okay, so what is asked here? Just like mean value of the load voltage. So what is the mean value of the load voltage? V naught equal to D times VDC. What is the D? 0.8 into 60. So it is 48 volts. So that's it. Okay, so moving on to the next. The chopper is used for on-off control of a separately excited DC motor, has supply voltage of 230 volts DC. An on time of 10 millisecond, off time of 15 millisecond is used for the chopper. Calculate average load current when motor speed is 1500 rpm. The motor voltage constant is 0.0 volts radian per second, and armature resistance is 0.3. Okay, so now again it is a motor application. So as we discussed in case of rectifiers, we discussed like 3 equations with respect to the motor. So one is output voltage or armature voltage, which is function of rectifier or chopper, whichever the circuit. Here chopper means it is a function of duty ratio. Then I naught, it is a function of torque. Then back EMF, it's a function of speed. So, and we have the relation among these. That's nothing but it's a motor application, means VR is equal to back EMF plus I naught R. So that's it. So we need to establish the things with respect to this, and we need to calculate. So we'll see. Okay, V naught. It is a function of duty ratio that is decided by the which chopper is connected. It is a step down chopper, so nothing is specified in step down chopper. In that case, we can calculate V average. V average is equal to, it's a duty ratio D into V naught. What's the duty ratio? It is on duration divided by total duration. That means 10 divided by 25 multiplied with input voltage 230. Okay, that we need to calculate what is the value of this. Okay, it's a 92 volt by calculating this, and I average is we need to calculate because average load current when the motor speed is. To calculate the I average, we need to use this equation. Okay, because torque is not given, that's why we need to calculate from this. To calculate this, we already have the V average at the required condition. We need to calculate back EMF at the required condition. So back EMF we need to calculate at 1500 rpm, and motor voltage constant is given. But motor voltage constant is given volt per radian per second. That means it is nothing but K dash. Okay, it is given as a K dash, it is not K. So in that case, back EMF is K dash into omega. So how to calculate? K dash is given 0.5 volt per radian per second, and omega we need to substitute in the in the radian per second. 1500 into 5 by 30. Okay, we need to calculate this one. Then it is 78.54. From now, using this equation, we can calculate I average. I average is 92 volts. That means V average minus E by R. So minus 78.54 divided by resistance. It is given 3. So now calculate that value. It's a 4.49 ampere. So that's it. Again, 3 equations only, but we need to consider these equations based on what circuit is given and what information is given. Okay, moving on to the next question. The separately excited DC motor in the figure below has rated armature current of 20 ampere and rated armature voltage of 150 volts. An ideal chopper switching at 5 kHz is used to control the armature voltage. If LA is 0.1 millihenry, RA is 1 ohm, neglecting the armature reaction, the duty ratio of the chopper to obtain 50% of the rated torque at rated speed and rated field current is. So this is a chopper is given, it is again step down chopper. In this case we need to calculate what will be the duty ratio at the required conditions. But here back EMF constant is not given, that's why we need to calculate using the rated conditions and required conditions. So to calculate that, so here you can see that what we need to calculate, duty ratio. How to calculate duty ratio? We have only one equation. What is that? V average is equal to D times VDC. We know the VDC. If you know the V average at the required conditions, then you can calculate the duty ratio. But how to calculate the V average? We have that another equation. What is that? V average is equal to back EMF plus I naught R. So we need to substitute these values at the given conditions. Okay, to calculate that, first we need to calculate here, we need to look at that what conditions are asked, because you know that back EMF is function of speed, it is function of speed, and I naught is function of torque. So we need to look at that. So back EMF is function of speed means what is the required speed now here? It is rated speed. So that means this back EMF is rated back EMF. So this is rated one. We need to calculate how to calculate rated one and all. We'll see that. So then what's that? I naught is function of torque. So now here it is rated torque. How much rated torque? 50% of the rated torque. So it is directly proportional. That means we need to consider 50% of rated current. So 50% of rated. We already have the rated armature current. What is the rated armature current? 20 ampere. So we need to consider 50% of that. That means half of that. So that's it. So we need to substitute this one. Resistance is already given. Back EMF we need to calculate at rated. So how to calculate that rated one? So rated back EMF always will be depending on rated values. It is already given. So rated armature voltage is given, rated current is given. We need to calculate that. Rated armature voltage is 150 minus rated armature current is 20 ampere into resistance is 1. So that means 130 volts. So now substitute here required V average. Okay, so if you want to calculate, that means required V average. What is that? It is rated back EMF plus 50% of rated torque, that means 50% of rated current, that means 10 ampere into 1. So 140 volts. Now substitute in this, get the duty ratio. Duty ratio is nothing but required voltage divided by source voltage. Source voltage is 200. So that means 14 divided by 20, 7 divided by 10, that means 0.7. So that's it. So these are the things we need to use to calculate this. Okay, moving on to next. A step up DC to DC chopper has input DC voltage of 220 volts. If the output voltage required is 330 volts and non-conducting time of the thyristor is 100 microsecond, the on time of the thyristor would be. So that means T off is given, we need to calculate T on. So to calculate T off or anything, first we need to know the duty ratio. How to calculate the duty ratio? Based on what circuit it is given. So here it is step up chopper is given. So in case of step up chopper, V average is equal to VDC divided by 1 minus D. So from this 1 minus D equal to VDC divided by V naught. So from this D equal to 1 minus VDC by V. That's nothing but V naught minus VDC by V naught. So remember that. Okay, there is a duty ratio in case of step up chopper. Now substitute the given things. Once you substitute, then you will get the duty ratio. What is the duty ratio? It is nothing but V0 required voltage is 330 volts minus VDC is 220 volts divided by again 330. So that gives it's 0.333. Okay, that's the duty ratio. But we need to calculate the on duration. How to calculate the on duration? That's very important. Okay, so either you can calculate using analytical methods, or you can actually directly substitute this one. So D is nothing but T on divided by T on plus T off. So we know T on, we know T off, we can calculate T on using duty ratio. Okay, so if you want, you can restructure this in a different way. Okay, so from this equation you can get that T on by T off equal to D by 1 minus T. You can also get this one in a different way also. If you remember what we discussed in SMPS, same thing you can discuss. What I told you that T on equal to D times T divided by T off. What I told you, T off equal to 1 minus D times T. So T gets cancelled, you will get the same thing. So now we need to substitute the things and then get the value. So from this T on equal to D that we calculated 0.33 divided by 1 minus 0.33 into T off. T off we already got that, it is a 100 microsecond. Micro. Okay, so that's what is given, 100 microsecond. Now you can get the T required on duration of the stopper. On duration is nothing but it will be 50 microsecond. Okay. In the circuit shown in figure, the input DC voltage has constant value Vs. Output voltage V0 is assumed ripple free. The switch S is operated with a switching time period T and a duty ratio T. What is the value of D at the boundary of continuous and discontinuous conduction of inductor current IL? So first we need to look at what circuit diagram is given. Okay, this question is related to SMPS. In case of SMPS, at the last slide I told you how to identify the given circuit is a buck converter or boost converter or buck boost converter. Okay, so for that we need to look at the inductor location. Look at that, inductor location is here. What is that? It is there on the source side or it is there on the load, it is there on the load side or it is there on the source side. In this case it is given on the load side. If it is given on the load side means this is buck converter. Okay, that's the first point. Second point, what we need to calculate? We need to calculate what is the D at the boundary of continuous and discontinuous. At the boundary of continuous and discontinuous, okay, continuous and discontinuous conduction, that means that is nothing but critical conduction. Okay, this question is given in one of the GATE exam. So critical conduction, boundary of the continuous and discontinuous conduction of inductor current is nothing but critical conduction. We already discussed critical conduction in the all three circuits. Now here it is asked what is the critical conduction duty ratio value. Okay, for that first we will take that what we have discussed the formula. From that we need to derive the D. We discussed in the buck converter critical conduction in terms of the inductance L equal to 1 minus T R by 2F. But here by looking at the options, instead of F we have the T, that's why I am taking this 1 by F as a T. So 1 minus D RT by 2. So that's what I am take care. Now from here we need to take the D out. Okay, so from this 1 minus D is equal to 1 minus D 2L divided by RT, 2L divided by RT. So from this critical DT ratio is nothing but 1 minus 2L by RT. Okay, this is the one. That means this is the minimum duty ratio required to have the critical conduction. Nothing but it's a just continuous. Nothing but it's a boundary of continuous and discontinuous. So for that we need to look at which option is correct. So this one. Okay. Next, move on to the next question. In the circuit shown, the ideal switch S is operated at 100 kHz with a duty ratio of 50%. Given that delta IC is 1.6 ampere peak to peak and I naught is 5 ampere DC. The peak current in S is, okay, so again we need to look at that because in the given question nothing is mentioned about the what circuit it is. Again we need to look at the position of the inductor. So the position of the inductor here is on the load side. That's why this is nothing but buck converter again. Okay, so what is given here? Delta IC is given. Remember, in case of buck converter we already discussed delta IC is nothing but delta IL. That means peak to peak ripple in the inductor current and peak to peak ripple in the capacitor current are same. Why? Only peak, that means ripple current is flowing through the capacitor and inductor. No ripple current will be there in the load. That's the meaning. So this peak to peak ripple current is given. Now it is asked about that what is the maximum current flowing through the S. Okay, I told you while discussing all these circuits, so maximum current flowing through the switch or supplied by the source or flowing through the inductor, all are actually same. That is nothing but IL max. Okay, so IL max is nothing but IS max, that is nothing but IDC max. Okay, what is the equation for that we discussed? It is average value of the inductor current plus delta IL by 2. But in case of buck converter we can take that IL, average value of IL is nothing but average value of the load current plus we can directly take that this delta IL as delta IC by 2. So now substitute the values. So maximum current flowing through the switch is nothing but I naught is given 5 ampere and delta IC is given 1.6 divided by 2. That means 0.8. That means it is 5.8 ampere is the peak to peak current flowing through the S. So that's the answer. Move on to the next. In the following chopper, the duty ratio of the switch is 0.4. If the inductor and capacitor are sufficiently large to ensure continuous inductor current and ripple-free capacitor voltage, the charging current of the 5 volts battery under steady state is. Okay, so that means voltage across the load is constant and current flowing through the inductor is also constant. That means no ripple in the both the things. Okay, so that's what is given. So now asked about what is the charging current for this 5 volts battery. Charging current in the load or load current I average, both are same. So now it is asked about I average. Okay, further about that, what circuit diagram is given here and all. When I told you that it is like a back EMF load is there and all, I average is actually slightly different from resistive load. That's nothing but V average minus back EMF divided by resistance. So first we need to calculate V average. When you want to calculate the V average, we need to look at what circuit diagram is given. That means what circuit is, what converter it is. Again, inductor is connected on the load side, that's why it is buck converter again. Okay. Buck converter V average is nothing but D times VDC. So now calculate the values. So here V average is D times D is given 0.4, okay, multiplied with the source voltage, that's given 20 volts here. So that means it is 8 volts, okay. Then I average or charging current of the battery is nothing but 8 minus back EMF is given 5 volts by resistance 3. That means it is 1 ampere. Okay, so that's what. Next question. A self-commutating switch SW, this one, operated at DT ratio del, is used to control the load voltage as shown in the figure. Under steady state operating conditions, the average voltage across the inductor, okay, and the capacitor are respectively. So what is asked here? What is the average voltage appear across this one? That means what is the VL, average voltage, and ask about what is the average voltage across the capacitor. That's what I asked. I told you many times while discussing power electronics concepts, many times I told you that is nothing but for a given periodical current, average voltage across the inductor is always 0. So that's what. Okay, it doesn't matter which circuit it is and all, this statement is true. So that's why this is straightforward. Average voltage across the inductor for the periodical current is 0. That is why this option is not correct, this option is not correct, eliminated. Okay, either of these two is the answer. Okay, now average voltage across the capacitor is nothing but average voltage across the load. Okay, because both are connected parallel. Indirectly, average voltage across the capacitor is nothing but load average voltage is asked. So load average voltage depends on the circuit diagram. So now we need to look at what circuit is given here. Okay, what circuit is given? That's where we need to look at the location of inductor. Now this time this inductor is connected on the source side. On the source side it is connected. That's why this is boost converter. In case of boost converter, what's the V average? V average is nothing but VDC divided by 1 minus del. So now look at these two things. Okay, this is actually not for the boost converter, this is buck boost converter. That's why this is the answer. Okay, so remember, main things is like in this case, in this diagram, average voltage across the capacitor is nothing but load average voltage. Average voltage across the inductor for the periodical current, this is always same whatever the circuit it is. This we have been discussing. Okay, so that's why I gave this question. Next one, a buck converter. Okay, already converter name is given. Feeding a variable resistive load is shown in figure. Variable resistive load. The switching frequency of the switch S is 100 kHz and the duty ratio is 0.6. The output voltage V0 is 36 volts. Assume that all components are ideal and the output voltage is ripple free. The value of R that will make inductor current just continuous. Okay, so that's what we need to calculate. Just continuous. First thing you need to remember, just continuous. Just continuous is nothing but critical conduction. Okay, so that's the meaning. Just continuous or boundary between continuous and discontinuous, critical conduction, all are same. Now it is asked about that what is the resistance value required at the critical conduction. So we need to use the same equation what we discussed. Critical inductance is nothing but 1 minus d R divided by 2F. So from this we need to take out the R. So R equal to, so from this 2FL divided by 1 minus D. Then we need to substitute the values. So R equal to 2 into F is already given 100 kHz, okay, into inductance is given in the circuit diagram. Okay, it is 5 into 10 to the power of minus 3 divided by 1 minus D. D is given 0.6 here. Okay, we need to calculate what is the resistance value based on this. Okay, so it is 2500 ohm. Then move on to the next question. In the circuit shown, all elements are ideal and the switch S is operated at 10 kHz and 60% of duty ratio. The capacitor is large enough so that ripple across it negligible, and at the steady state acquires a voltage as shown in figure. That means at steady state voltage, this is nothing but more or less average voltage across the capacitor and load. The peak current amperes drawn from 50 volts DC source is. Okay, that's what we need to calculate. So here again asked about the peak current supplied by the DC source. Okay, so that means it is asked here what is the peak value of this ID max. We already discussed in the previous question ID max equal to IS max equal to IL max. So power. So that means in all the SMPS circuits we discussed, IL max is nothing but IL plus delta IL by 2. That's what. So IL and delta IL by 2 depends on what circuit diagram is given here. So if you look at here, to identify the which circuit diagram is given, we need to look at inductor location. Inductor is neither connected on source side nor connected on load side. So that's why here it is in the middle. If it is in the middle, then it is buck boost converter. Okay, buck boost converter. In case of buck boost converter, I told you IL average inductor current is neither equal to I0 nor equal to IDC. That's why you can calculate this IL in different way. That means IL equal to I0 divided by 1 minus D. That's a 1. And delta IL also we need to calculate. Delta IL is VDC into, you can see that whether T is given or F is given. It is F is given, so into D by FL. Okay, so based on that we need to calculate the values. But how to calculate the IL? IL you can I naught you can calculate. How to calculate IL? IL is I naught by 1 minus 2. But how to calculate the I naught? I naught is nothing but V naught by R. So how to calculate the V naught? In case of buck boost converter, V naught is nothing but D by 1 minus D into VDC. But remember, so we need to look at the polarity here. So polarity is actually this must be positive, this must be negative. Otherwise, negative sign will be there here. Okay, that's what. Now we got the required equations. We need to substitute the given values in this, and then we need to get the answer. Okay, so now I'm calculating all the values here. You can look at that. So first we need to calculate V average. So V average is nothing but D by 1 minus D. D is given 60%, nothing but 0.6 divided by 1 minus D, 0.4 into 50 volts. In fact, that's already given. Okay, I told you that D is more than 0.5, it will act as a boost converter. That's why you can see that it is more than 0.5. That's why 50 volts to it is increasing to 75 volts. Again you will get the same thing only, like 6 by 4 is nothing but like again 3 by 2, then it will be 25 times it will be 325 is nothing but 75. Okay, it's already given, but I am calculating again. Then from this we need to calculate I naught. I naught is nothing but V naught divided by R. R is given 5. 75 divided by 5. 75 divided by 5 is nothing but 15 ampere. Okay, so from this we need to calculate again IL. So IL is nothing but 15 divided by 1 minus D, nothing but 0.4. Okay, so that's what we need to calculate. So it is 37.5. That's IL. Next we need to calculate delta IL. So what is the delta IL? Delta IL is VDC. VDC is nothing but 50 into D. D is nothing but 0.6 divided by FL. F is like 10 kilohertz. So 10 into 10 power 3 into L. L is given 0.6 millihenry. 0.6 into 10 to the power minus 3. Okay, so this and this gets cancelled. 0.6 gets cancelled. 50 by 10 is nothing but 5 ampere. Now we need to calculate IL max or IS max. All are same. Okay, IS max. IS max is nothing but IL plus delta IL by 2. IL is already we calculated 37.5 plus delta IL by 2. Delta IL we calculated 5 divided by 2, 2.5 ampere. That means it is 40 ampere. So that's answer. Okay. Moving on to the next question. For the switching converter shown in following figure, assume steady state operation. Also assume that components are ideal, inductor current is always positive and continuous, and switching period is Ts. If the voltage VL is as shown the duty cycle of the switch is. This is a converter is given, this is a inductor voltage is given. We need to calculate what is the duty ratio. Without knowing anything, we can calculate simply duty ratio by using only one concept. What's the concept? We discussed many times. There's nothing but average value of the inductor voltage is 0 for the periodical current. So this is having like this means current will have obviously periodical current, then obviously we can take this one. So you can take this area under the curve divided by time period. So this we know that T on can be taken as, this is T on, okay, this T on can be taken as a dt, and this is T off can be taken as a 1 minus d times t. Okay, that's what. So using that you can calculate. So that means here area under this curve 15 multiplied with dt, okay, 15 multiplied with dt plus, but here it is a negative area, that's why you can take minus, okay, 45 into 1 minus dt whole divided by time period t equal to 0. So t gets cancelled, you will have 15d minus 45 multiply this one, 45 minus half minus plus 45d equal to 0. So you can see that 60d equal to 45, 60d equal to 45, then d equal to 45 divided by 60, that's it. Okay, there's nothing but 3 by 4, 3 by 4 is nothing but point, okay. Okay, 0.75, that's a deviation. So now we can, okay, this is what I don't know, then I wanted to calculate based on the given things and all, maybe like a given circuit. Yes, we can calculate using that also. Okay, we'll try again with a different way. So you can see here, okay, you can see here given circuit diagram. What is the circuit diagram here? So inductor is connected on the source side, that's why this is boost converter. Okay, boost converter. So that's what, remember. Now here you can see that when switch is on, you can see this source voltage is connected to the inductor. That means it is getting charged. During that time, inductor voltage is nothing but source voltage. That means when switch is on, that's nothing but T on, you can see this voltage is nothing but VDC. When switch is off, this input voltage plus inductor voltage, in that case this will be discharged, that's why it will be negative. That means this will be minus, this will be positive. Both will supply the energy to the load. In that case, Vin, that means VDC, plus VL equal to V0. That means VL is nothing but V0 minus Vin. So this is negative is okay to represent on the negative side. Forget about that. This negative is not important. That means this 45 volts is nothing but V0 minus VDC. That's it. Okay. If you know the operation of this converter, you can get that. So from this, we already got that VDC equal to 15 volts, and from this V0 minus VDC equal to 45. Okay, so from that you can get that V0 is 45 plus VDC, that's nothing but 60 volts. So that's it. So I already told you that boost converter V0 equal to D times V0 equal to VDC by 1 minus T. So from this one you can calculate D equal to V0 minus VDC divided by V0. This we already discussed in the beginning of that means in the chopper circuits. Okay, beginning of this DC to DC converter questions. So now if you substitute all these things here, you can get the same thing, V0 minus VDC, that we already know that 45, okay, divided by V0 is 60. So you can see that again it is coming to the same thing. So that means it is 3 by 4 is 0.75. That's it. You can calculate either using the operation of this one by looking at equivalent circuit diagrams. We discussed many times for equivalent circuit diagrams. That's why each and every point is important what we discussed in case of SMPS. That's what again I'm telling you. Whatever we discussed, the three circuits, boost converter, buck boost converter, everything, equivalent circuit, waveforms, formulas, all are important. Based on all these things, questions are there in the GATE exam. So that's why you can either understand each and everything. If you're actually facing the difficulty, let me know. We can discuss some of the things again, or you can by heart some of the things and then answer the GATE questions. Okay, you can solve. There are many other GATE questions also. You can solve that. If you're not getting the answer, let me know. We can do that. Okay, move on. In the figure shown below, the chopper feeds a resistive load from a battery source. MOSFET Q is switched at 250 kHz with a duty ratio of 0.4. All elements of the circuit are assumed to be ideal. Okay, this circuit diagram is given. The average source current in amperes in steady state is. Okay, so again, first thing what we need to do, what is the given circuit it is, to calculate the source current. To calculate the source current, first of all we need to find out what is the circuit diagram means. Look at that where the inductor is located. Inductor is located on the source side. How to find that whether it is on the source side or not? When you turn on the switch, it is connected to the source. When you turn on the switch, it is still connected to the source. That means it is always connected on the source side. If it is connected on the source side, then it is boost converter. Okay, so boost converter, we already discussed power balance equation. What's the power balance equation? V0 by VDC equal to IDC by I0 equal to 1 by 1 minus T. So this relation will give you the kind of like a voltage relationship or current relationship. You can do that. Okay, power balance equation, that means if you cross multiply source power IDC VDC equal to load consumed power V0 I0. So that's what. So now to calculate the first thing, we can actually look at here, what's that average source current we need to calculate. Average source current, if you want to calculate, means use this one. So here IDC equal to I0 divided by 1 minus T. But how to calculate the IDC? I0. I0 is nothing but V0 by R. How to calculate the V0 in case of boost converter? It is VDC divided by 1 minus T. That's it. Okay, you can substitute all the things in the bottom to top approach. You will get that things. Okay, so we can calculate V0 equal to VDC is 12 volts from the circuit diagram divided by 1 minus D. D is 0.4. So you can see that 1 minus 0.4, 0.6, 12 divided by 0.6. Okay, so that's nothing but like 120 divided by 6. So it is nothing but 20. Then I average. I average is nothing but V average divided by resistance. Resistance is given in the circuit diagram 20. That means it is 1 ampere. So from this, what is the average value of the source current or DC current? So IDC equal to I0 1 ampere minus 1 minus T, it is 0.4. That means it is 1 by 0.6. 1 by 0.6 is 10 by 6. 10 by 6 is 5 by 3 ampere. Okay, so that means this is the answer. Now there is another question. We need to answer that one. What is another question? Peak to peak source current ripple in amperes. In case of boost converter, peak to peak ripple in DC current is same as peak to peak ripple current in the inductor. Okay, that is equal to VDC into D by FL. So that you can substitute. So if you substitute that one, then you will get, what is that? VDC is given 12 and duty ratio is 0.4 divided by, so F is nothing but 250 kHz and L is given 100 micro Henry. Okay, so that gives it is 0.192 ampere. So that's it. So this is the answer. Okay, so with this I am stopping SMPS circuits, and finally we can conclude it's a completion of the power electronics. So I can say like this is a kind of advantage for you. You can keep on look at that videos and then understand the things and then utilize the opportunity. But I'm sincerely telling that if you're facing any issues, let me know. We can discuss further. If you're actually telling some other questions which you're not able to understand, then I can answer you through videos. We can see that. But you have to put a lot of time to understand the things and then look at the videos again and again and then get the concepts. Okay, so all the best, and we can discuss if at all anything is required. Otherwise I can say these are the things sufficient for the power electronics for the GATE exam. Thank you. Okay, once again, all the best.